Welcome back. In the previous videos, we looked at a few introductory ideas on the topic of viscous flow in pipes. In particular, we looked at some general characteristics. We discussed the onset of turbulence, the idea of the fully developed region and the entrance length, and finally we derived the expression for the pressure loss in a straight pipe section given over here. In this video, we're going to formalize this idea with the concept of the head loss in pipes. So we saw that for a laminar flow, the friction factor has a nice analytical relationship given by 64 over the Reynolds number. For a turbulent flow, the friction factor is a function of the Reynolds number and the roughness of the pipe. And we know that we can get this friction factor for a turbulent flow using a Moody diagram. So head loss is defined for a horizontal pipe section using this expression over here. So the head loss is the delta P divided by the density and the gravitational acceleration. So using the expression derived in the previous video, the head loss for a straight pipe section is given by this expression over here. And as you'll note, the head loss given by H subscript L has units of length. So what is this head being lost? Let's consider a section of pipe. We're going to consider a streamline going from point 1 to point 2. Now what is happening between points 1 and point 2? We know that the velocity stays the same. The elevation is the same. But we know from our expression over here that the static pressure decreases. So recall that we have this expression for what we call the total pressure, where the total pressure is equal to our static pressure plus 1/2 rho v squared plus rho gz. So this sum over here is constant. This over here decreases, and therefore the total pressure decreases as well. So, what does this tell us? For a real pipe flow, the total pressure decreases. But for, let's just say for an ideal flow, using Bernoulli, the total pressure is constant. So as we can see, Bernoulli's equation is not, strictly speaking, valid for viscous pipe flows. So what we call the head is similar to the total pressure. So the head is given by P over rho g plus V squared over 2g plus Z1, or plus Z. And the head loss is what we see between 2 points. So the difference in the head between point 1 and point 2 somewhere along a pipe section. And as mentioned, that head loss can be expressed as a friction factor multiplied by L over D multiplied by V bar squared over 2g, where V bar is our average velocity. So if we were to look at something h1 minus h2, it would look something like this. We have P1 over rho g plus V1 squared over 2g plus Z1 minus the head loss is equal to P2 over rho g plus V2 squared over 2g plus Z2. And all of this is applicable for, well, this is for a straight pipe section. And this over here looks like a modified Bernoulli's equation. And indeed it kind of is. And what we call this here is the mechanical energy equation. And as we can see, for a straight pipe section, which has no elevation change, and between 2 points the velocity remains the same, we recover our HL being equal to that delta P over rho g. So now we turn our attention to major, or to the distinction between major and minor losses in pipes. So major and minor losses. So what we define as a major loss is the pressure loss that we encounter in straight sections of pipe with fully developed flow. So let's write this out. Losses in straight pipe sections with fully developed flow. And this is what we have focused on so far. So our derivation for our pressure drop delta P was only considering the mechanical energy losses due to the effects of friction. But what we also know is that we have another type of loss, which we call a minor loss. And these minor losses are losses due to different fittings, valves, and expansions, contractions that we might encounter in our system. So these are losses due to fittings, valves, sudden expansions, etc. Okay, so to recap, we have major losses in straight pipe sections of fully developed flow, and minor losses in the various geometric and other properties that we might encounter in our system, such as valves, expansions, contractions, things like that. So what we can actually say is that the head loss between 2 points is equal to the head loss due to major losses plus the head loss due to minor losses. So far we have only focused on this first type of head loss. Recall our derivation did not consider any types of bends or sudden expansions or anything like that. And in fact, these minor losses are not really easy to derive. In fact, they are experimentally determined. So oftentimes, these extra losses are due to flow separation. There's dissipation of energy when this occurs. And we can also say that it is determined experimentally and tabulated. So these minor losses are characterized by what we called loss coefficients. So characterized by loss coefficients. So what does this look like? The minor losses are given by a loss coefficient KL multiplied by V bar squared over 2G. So we can see that this compares quite closely to our expression for major losses, which is given by the friction factor multiplied by L over D multiplied by V bar squared over 2G. And so again, this is for a straight pipe section, straight section, and this is here minor losses due to fittings and expansions, contractions, etc. And what we found experimentally is that these loss coefficients seem to be only functions of geometry. Or rather, we should be a bit more specific, and they are much stronger functions of geometry and less so on Reynolds number and surface roughness. Whereas, as we know, the friction factor is a function of Reynolds number and surface roughness. And so here are tabulated several loss coefficients. So in the left image, we see loss coefficients for various fittings. So here we have 90-degree elbows, 45-degree elbows, T-valves, and different things like that. In the middle image, we see the loss coefficient due to a sudden expansion. So when we encounter a sudden expansion, what we get here is this recirculating zone over here. And this is due to flow separation, and it is highly dissipative. And so we can see that our loss coefficient KL is dependent on the area ratio A1 over A2. And again, for a sudden contraction, similarly, we see that the loss coefficient is dependent on the area ratio, but take note that now we are looking at the area ratio A2 over A1. Finally, we see loss coefficients, KL, for an entrance, and dependent on the radius of the edge of the entrance. Okay, so all of these loss coefficients can be used in our head loss equation over here, which can be used in our mechanical energy equation. Finally, I want to present the most general form of the mechanical energy equation. In fact, we can add energy to our system, and this is often the case. For example, we see a lot of piping systems where we have a pump somewhere in the network. So this indeed is adding energy to the system. So how do we account for this in our mechanical energy equation? Well, it'll look something like this. So we still have our modified Bernoulli's equation where we're dividing by the density and the gravitational acceleration. So P1 over rho g divided or plus V1 squared over 2g plus Z1. Now recall that we had the head loss over here, and this is still present. So as opposed to the head loss, which is extracting energy from the equation, here we have the addition of energy, HP, and this could be something in the form of a pump head. And this is our head loss. And again, due to both major and minor sources over here. And this is finally equal to P2 over rho g plus V2 over 2g plus Z2. So just like head loss, HP has units of length. And in fact, many pump manufacturers will give you the pump head. Finally, the pump power, where power is the rate of work, is equal to the pump head multiplied by rho g and then multiplied by the volumetric flow rate Q. So in this video, what we have done is that we have formalized our pressure losses in pipe by making the distinction between major and minor losses. We introduced the concept of head loss, noting that we have major losses due to friction occurring in straight pipe sections in a fully developed flow, and we have minor losses due to pipe fittings, expansions, contractions, etc. Then finally here we have the most general form of the mechanical energy equation, which has units of length, and here we see that we have terms for the addition of energy to the system, and we have our head loss term HL, which extracts energy from our system due to friction and minor losses.